we will look at the, we will continue what we were doing. We look at the 3D z square orbital. As I told you, this is the polar plot in the xz plane, and if you wanted to get the 3-dimensional appearance, you have to take this figure and rotate it about the z axis. Okay. And further, I also told you that in the direction with theta equal to cos inverse of 1 by root 3, you can actually calculate it, it will turn out to be 54.73 degrees. You will find that the value of the function is 0. So, if you marked that direction in this figure, what you are going to get is a line, okay, along this line such that this angle is equal to 54.73, the value of the function is 0, and similarly along this direction. But why along those two directions only? You think of a direction downward like that, over a direction there on the other side, right, such that this angle is how much? It is actually 180 minus 54.73. Again you will find that cosine of theta will be equal to 0. Okay. So, when you get the 3-dimensional appearance by rotating about the z axis, you think of what will happen to these lines. These lines actually will describe a cone, something like that, such that the internal angle, this angle of the cone is 54.73 degrees, and similarly these lines will also describe another cone. And you should realize now that for any point lying along the surfaces of these cones, the angular part of the wave function will be identically equal to 0. And if the angular part is identically equal to 0, what will happen? The wave function itself will be equal to 0, and therefore, if I think of the total wave function, the total wave function has two nodal surfaces, right? They are surfaces, the two nodes. Where are they? One is actually along the surface of a cone, right, such that the interior angle, this angle within the cone is equal to 54.73 degrees, and the vertex of the cone actually is pointing down. And similarly, there is another cone whose vertex is pointing up. Along the surface of that cone also the wave function will be identically equal to 0, and hence you have another nodal surface. Okay. So, with this information, let me show you a polar plot of this orbital. This is the appearance which is obtained by rotating this figure about the z axis. Okay. So, these two things actually they are describing something that is shaped like a donut, though not exactly, but you can see the appearance from the figure. I can if you want, I can rotate it a little bit. See, this is how it would appear, and if you looked from above, roughly that is how it looks like. Okay. From any angle you can view it. So, this is 3D z square orbital. The orbital is referred to as 3D z square, and you can also make a density plot if you like. So, how will you make the density plot? I can do it here. Well, the first thing that I will now do is label the axis. This is, let me say, the y axis if you like, and this is the z axis. Now, in this direction actually the wave function is positive, but then along that the two special directions, these are the special directions, along them the wave function is 0, and similarly along these directions also the wave function is 0. So, why do I mark the line directions along which the wave function is 0? Because you see, if the function is positive, as soon as I cross this line the function function will change sign. So, the on this side what will happen, the wave function is going to be negative. This is positive. And then when again I cross this line, what will happen, the function will again change sign. So, therefore, in this region the function will be positive, and then again in this region the function will be negative. So, that is how the appearance of the function would look like if you made a density plot. This is positive, that is negative, this is positive, and that is negative. So, using the software Mathematica, I do have a plot of this function, a density plot. Let me just draw it. Okay, here it is made in the xz plane, but it does not matter whether it is in the xz plane or whether it is in the yz plane, the appearance will be the same. You will see that in this region the function is positive, in this region the function is negative, sorry, again positive. In these blue regions, the way they are represented, in these blue regions you can see actually the value is negative, that is clear. When I point to one of the lines, you see this is the line along which the value of the function is negative, and it has a value of minus 0.3. So, this is the appearance of the 3D z square atomic orbital. Okay. Then we have to worry about other atomic orbitals. I will not be actually writing down the functions, but perhaps I can just show you the polar plots of these other functions, and that should be enough. Any orbital that you want to see, it is easy to make a polar plot. This is actually the orbital that is referred to as a dxy. How will you get them? The procedure is just the same as that I have outlined. You have to put other values of m, psi 3 to plus or minus 1, but if you put plus or minus 1, the result is going to be complex. So, therefore, you will take either the cosine function or the sine function and then proceed. Okay. And the results are actually 5 orbitals in total, because you have m equal to 0 plus or minus 1 plus or minus 2, you have 5 orbitals in total, and those 5 orbitals actually the convention is to label them as 3D xy, 3D yz, 3D xz, then 3D z square I have described, and there is another orbital which is denoted as 3D x square minus y square. Okay. And you can make polar plots of all these orbitals. So, 3D xy is the one that you can see here, as you will see in the picture. See, this is your z direction, you have the x and y axis, and you can see that this has 4 lobes, right, which are clear in the picture, and these 4 lobes are pointing in between the axis. The important thing is to realize that the orbital is in the xy plane, it is in the xy plane, it is lying in the xy plane, and there are 4 lobes. Maybe I can draw this on the board. Imagine this is the xy plane. So, you have one lobe here, another one there, another one here, and the 4th one there, and it so happens that this and that are plus. In these directions the wave function is positive, while in these directions the wave function is negative. Okay. So, that is how it is. So, 3D xz, what will happen? The appearance is the same except that it is in the xz plane. The orbital is lying in the xz plane. It is very similar to xy except that the everything is now in the xz plane. And of course, this has a both of these orbitals has two nodal planes. Where are the nodal planes? Just to illustrate, in the case of this orbital which I have denoted xy, right. In this case, remember the z axis is standing perpendicular to the plane of the board in this fashion. So, if you think of such a plane, which is what plane? It is the xz plane, or you think of such a plane which is nothing but the yz plane, then these are actually nodal planes. Similarly, if you think of this orbital, you would realize that the xy plane, right, the xy plane is a node and the yz plane also is a node for this orbital. So, then we have seen xy and xz, we should also see yz, almost the same except that this is now in the yz plane. Okay. Then we have only one more orbital left. What is that? It is actually the orbital that is called x square minus y square, dx square minus y square, this one. How does it appear? You can see that this is the appearance. The important thing is to notice that these are not lying in between the axes, but if you look at it, you would see that these are actually lying along the x and the y axis, right. I shall now draw the dx square minus y square orbital, showing you clearly the positive and the negative lobes of this orbital. So, these are my axes x and y, and the orbital that I am drawing is dx square minus y square. It will have a positive lobe like this and another one in exactly opposite direction, and it also has two negative lobes, one is like that and the other one is like this. And let me put the signs of these orbitals, signs of these lobes. There is a negative sign here, negative sign there, these are negative regions for the wave function, and you have a positive lobe here, another positive lobe there. And the important thing is to notice that if you performed the operation of inversion, the orbital would remain unchanged. And people normally say that this is an orbital that is symmetric under the inversion operation. So, that is all regarding these orbitals. So, how many of them in total? You have 5 of them, corresponding to m equal to 0 plus or minus 1 plus or minus 2. Then when you think of n equal to 4, again I am not going to describe n equal to 4 in all its details. When n is equal to 4, you would have the 4s atomic orbital. I am not going to describe it. You will have 4p, 4s atomic orbital, there is only one 4p, there are 3 of them, they will be 4px, 4py and 4pz. Okay. Then we will have L equal to 2, you will have 4d, there will be 5 of them, their appearance everything is similar to the 3D orbitals that we have just now described. Why? Because the angular part of the wave function is just the same. But then when you have 4f, this actually will correspond to L equal to 3. Okay, when L is equal to 3, you have the 4f orbitals. There are how many of them? There are actually 7 of them. Why? Because m can take on the values 0, plus or minus 1, plus or minus 2, and plus or minus 3. Okay. So, there are 7 atomic orbitals, all of them have precisely the same energy. In fact, in the case of the hydrogen atom, all these orbitals have precisely the same energy, and if you counted them, how many are there? 7 f orbitals, 5 d orbitals, 3 p orbitals, and 1 s orbital. So, the total number is 16, which is actually equal to n square, where n is the principal quantum number, n in this case is 4. So, if you have n a particular value, then there are n square orbitals having precisely the same energy. Then what about the 4f orbitals? What about their shapes? Well, the shapes are actually given in many textbooks. I can use Mathematica and show you the shapes of these 7 f orbitals. I will show you the shape of one particular set of the 7 f orbitals. I mean, if you look into a book, a textbook like the book by Hughey on inorganic chemistry, you will find that he gives you 2 different sets of f orbitals. So, people have I mean 2 sets of f orbitals, one set of 7 and another set of 7. These are actually not independent of each other, because one can be expressed in terms of the other. So, what I am going to show you is referred to as the cubic set. So, the cubic set actually consists of these 7 orbitals, which I will list first and then show you how their shapes are. They are actually written as fz cube, fx cube, fy cube. Then the next orbitals are fx into y square minus z square, f y into z square minus x square, and f z into x square minus y square, 3 of them, and then finally f x y z. So, these are the 7 orbitals that I will show to you. But before I show it to you, that actually you may ask, why do you use this impulse? For example, in the case of dxy, why do I write the orbital as dxy? Right, that is a natural question that one would have. The answer is actually very simple. What you should do is, you should take x is given by this expression, and y is given by that expression, you multiply the 2. So, what will be x into y, it is actually going to be equal to r square sin theta, or sin square theta actually, cos phi sin phi. That is the result, and you just look at the angular dependence of this product x y. The angular dependence is sin square theta cos phi sin phi, and that precisely is the y function. Remember, any orbital would have a y part, and this is just the y part of this orbital. So, when you write dxy, actually you are implying that you take the expression for x, you take the expression for y, multiply the 2 and remove the radial dependence, you will get the spherical harmonic corresponding to that function. So, when you see a symbol like dx f x y z, it is actually very simple. If you wanted to find out the angular dependence of this function, all that you need to do is multiply these things, right, and then throw out the r dependence. What is left is the angle dependence of the function. Now this is actually useful for this one, it is useful for this one, but with this it is a little bit more complex. What I have told you does not give you that, right. It is not applicable for d z square also, it is not applicable for d z square, but it is applicable for other orbitals. For all the other orbitals, this what I have told you is applicable. So let me now look at the f orbitals. First I will plot f z cube, I have to execute the command. So you will see that this is f z cube. It is similar to your d z square, but there are also differences. What are the differences? You can say, well, this lobe will be positive if you like. This is going to be, what about this one? If this is positive, this I would assume is negative, and so somewhere in between is a cone on the surface of which the wave function will be 0. Then if this is negative, the next one will be positive, again in between there will be a surface on which the function will be 0, and that in this case is very simple, it is nothing but the xy plane, right. And then if this is positive, what will happen? This other thing will be, well, let me repeat, plus, this is plus, this is minus, that is plus, and the last one will be negative, correct. And so how many nodal surfaces? Well, the answer is one here, another one in between these two, and the third one between those two. So therefore 3 nodal surfaces. So this is the appearance of the f z cube. Notice that it is oriented along the z direction, right. So if I put x cube there, all that will happen is that the appearance is going to be similar, except for the fact that it is oriented along the x direction, and that is what you are going to see. Okay, this is oriented along the x direction. Then you can have fy cube. This will be oriented along the y direction. Then let us look at f x y z. Interesting shape. Well, it is actually an interesting question to ask, how many nodal planes are there? It has 3 nodal planes. Where are they? You can see if you think of the xz plane, it is a nodal plane. You think of the yz plane, again you would realize that it is a nodal plane, and similarly the xy plane also is a nodal plane. So that is how this orbital is. I mean, if you are not convinced, actually I can rotate it in any direction I like. See, for example, here I am looking down along the z axis, right. See, if you are just looking down along the z axis, so there are actually 8 lobes for this orbital, and 4 lobes are sitting on top of the other 4 lobes, and therefore you can see only 4 lobes essentially. And you will see that along this direction, right. Remember, red color actually denotes the x axis, blue color is the z axis. Okay, so this is actually the blue color along with this x direction is actually the xz plane, and you can see that the function vanishes. Similarly, this is the y axis, the green color. So that is the y axis, and again the z and the y axis together, they form a nodal plane. So similarly, I can rotate it in any direction, and you would realize that there are 3 nodal planes. So let us now look at another orbital, which we may be, what do you want to call it? Let us say f x y square minus z square. or maybe what I will do is, instead of this I will first plot another one. See, if we look at this figure, this is your f x y z which we have looked at and understood, and this is the other orbital which I am plotting now. What is it? You have f z, the orbital is f z x square minus y square, that is the orbital that is being plotted. And if you looked at the two orbitals, what you should realize is that the appearances are roughly the same. In fact, if you inspect it closely, you would realize that this second orbital can be obtained from the first, if you like. How? By rotating this orbital about the z axis. You just take this orbital, rotate it about the z axis by 45 degrees. It might need some time to realize that, but all that you need to do is take this orbital, rotate it by 45 degrees about the z axis, you are going to get this orbital. Okay, that is how it is. So, therefore, the shapes, everything is the same, except that one is obtained from the other by rotating by 90 degrees about, sorry, not 90, but 45 degrees about the z axis. Similarly, if you took this orbital and rotated it about the y axis by 45 degrees, you will get this orbital. You will get this orbital. If you rotate about the y axis by 45 degrees, you will get this orbital, while if you rotated it about the x axis by 45 degrees, you are going to get this orbital. Okay. I mean, if you want to see them, I can obviously show them. Again, I will show just one of them, f x, that means I am rotating by the x axis. So, that is how these orbitals are. So, there are 7 of them. So, you have seen, as I have told you, what is referred to as the cubic set of f orbitals according to the book by Huey. The book is Inorganic Chemistry by Huey. Okay, let me summarize what I have told you regarding the hydrogen atom. We have completely solved the Schrodinger equation for the hydrogen atom, and we found that there were 3 quantum numbers arising in the process of solution. Okay, there were 3 quantum numbers arising in the process of solution. They are actually the quantum numbers that are referred to as n, l and m. N is referred to as the principal quantum number. It can take values like n is equal to 1, 2, 3, 4, etc. right. The other quantum number is L. It is referred to as the azimuthal quantum number. It can take the values 0, 1, 2, 3, etc. up to n minus 1. This condition actually arose automatically when we try to solve the equation. And the third quantum number is M, referred to as the magnetic quantum number. It can take the values 0, plus or minus 1, plus or minus 2, etc. and the maximum value actually will be plus or minus, well, the last possibility is either plus L or minus L. So, these actually arose out of our solution, but the energy depended only upon the principal quantum number. It does not depend upon the values of L and M, it simply depends only upon the value of N, and this is actually the case with the hydrogen atom. Okay, and then if I represented the allowed energy levels, N is equal to 1 has the lowest possible energy, that is the ground state. This will give me the 1s atomic orbital. N is equal to 2, there are 4 allowed orbitals corresponding to L being 0 and L being 1. This is N is equal to 2. Four orbitals. The next one is N is equal to 3. You can have L equal to 0, 1 or 2, and correspondingly how many orbitals do you have? In total you have 9 orbitals. So, I should represent that by drawing 9 lines very close to each other, that is difficult. So, I will not do it, but there are 9 orbitals. What are they? They are actually the 3s, 3p and 3d orbitals. In the case n is equal to 2, you will have 2s and 2p orbitals, and when n is equal to 4, you have 4s, 4p, 4d and 4f, 16 orbitals, right. They are all degenerate. So, typically, I mean, if I do not represent the degeneracy the way I would represent this, let me not worry about the degeneracy, because that is difficult to represent. This is n is equal to 1, this is n is equal to 1, that is n is equal to 2, then n equal to 3, maybe I am not drawing it correctly, because the energy separation has to be realistic. So, let me draw one more figure. This is n is equal to 1, then I have n equal to 2, this is a 1-fold degenerate, which means it is not degenerate, this is a 4-fold degenerate, then I have n equal to 3, 9-fold degenerate, n equal to 4, 16-fold degenerate, then n is equal to 5, 6, 7, 8. As you go up, the separation between the energy levels get closer and closer and closer. In the limit n tends to infinity, the separation becomes 0. So, therefore, somewhere here is energy 0, right. Here the energy is 0. We found only these solutions. Remember, in our analysis we said that the total energy of the system is negative, but then you may ask what will happen if the total energy is positive. Okay. So, the answer is actually extremely simple. If we have actually taken a situation where we have the proton, and if the electron is at infinite distance, there is no interaction between the two, and the energy of the system is 0. Okay. Now, how can you have an energy which is greater than 0? The answer is that the electron has to move with some energy, then it will have a non-zero energy, right. It has to move from infinity. Suppose I just push it, then it will move, it will have some kinetic energy, and the kinetic energy of the electron, if suppose that the electron is at infinity, I just give it some kinetic energy, it will come and it will visit, so to say, or it will collide, or it will get scattered by the proton, and after the scattering what will happen? It will go away, and the amount of kinetic energy that I can give is decided by me. I can give it any kinetic energy, and therefore, I can solve the Schrodinger equation with the electron having some kinetic energy starting with, it starts at infinity with some kinetic energy, comes near the proton and it goes away. And as I have told you, the kinetic energy that the electron initially has is determined by me. So, I can choose it to have any energy, and therefore, above this 0 actually you can give the electron any energy, and the energy levels are not quantized. It is possible to have any energy starting from 0 to infinity. These are what are referred to as the scattering states, in which the electron is simply scattered from the proton. It comes, hits the proton, it spends some time in the vicinity of the proton and goes away. So, this is how the allowed energy levels of the hydrogen atom are. Okay. And again, I should also remind you that we have just spoken of the bound states and the scattering states. But in addition to this, you have the hydrogen and the proton. Suppose they form the bound state, in which is what is referred to as the hydrogen atom, then the hydrogen atom can execute translational motion as a whole, right. That is something that we have not worried too much, but that also is there, just to remind you. But then of course, you see, you have already studied something about the nature of the hydrogen atom, and you would know that the 3 quantum numbers are not enough to describe the state of the hydrogen atom. In the case of in the case of hydrogen atom, 3 quantum numbers are not enough, you actually need 4 quantum numbers, and this 4th quantum number arises from the idea of spin, something that I will describe later. But before I do that, I want to do some general things, because we now have enough background to do a few general things. Now, you see, we have solved the Schrodinger equation for which systems, particle in a box. We have solved the Schrodinger equation for the harmonic oscillator. We now have solved the Schrodinger equation for the hydrogen atom. In all the cases, if you remember, it was possible to normalize the wave function. Wherever we had the solution, we can normalize it. That was not difficult. Then further, in the case of the particle in a one dimensional box, I did demonstrate to you that any two wave functions, right, they are orthogonal to one another, and I demonstrated that for the harmonic oscillator also. For the hydrogen atom, I have not demonstrated it, but it is possible to show that you give me a 1s atomic orbital, this 1s atomic orbital will always be orthogonal to the 2s, it will be orthogonal to the 2p. Right. So, therefore, if you give me any two wave functions which are solutions of the Schrodinger equation, then I take the first one, which I may denote as maybe psi 1, I will take the second one, I may denote it as psi 2. For example, this may be the 1s atomic orbital, this may be the 2s, or it may be the 2p, it does not matter. Let us take another atomic orbital, multiply the two together, and by the volume element d2 integrate over the entire space. The answer is going to be 0, and we say that these two functions are orthogonal. We have already seen this. We have also in our postulates, we have said that any operator that occurs in quantum mechanics has to be a Hermitian operator. We made that postulate. I mean, in the postulate, this was actually a part of the postulate. So, what is a Hermitian operator? The Hermitian operator is an operator, let me say A, for which what I will do is I will allow this to operate upon A, an acceptable wave function like psi, which I denote as psi, multiply it by the complex conjugate of another acceptable wave function, which I denote as phi, and then integrate over the entire space. Because I have done an integration over the entire space, the answer is going to be a number, the number may be complex. Okay. Now, suppose instead of doing this, I take A, allow it to operate on phi instead of operating on psi, and then multiply it by the complex conjugate of psi and integrate over the entire space. Okay. If it so happens, I mean, or if it is so that this number and that number are complex conjugates of one another for any acceptable psi and phi, then I define A as a Hermitian operator. This was our definition of a Hermitian operator. Okay. And what are the properties of Hermitian operators that are of interest to us? The most important thing is that their eigenvalues are always real. Now, I am going to prove that if I have a Hermitian operator, then any given eigenvalue of that Hermitian operator has to be a real number. That is what I am going to prove now, right. I mean, I could have done the proof earlier, but I thought it is best to do it at this point, because you do have some familiarity with orthogonality, normalization and related things. So, it will not appear as abstract as it would have appeared earlier if I had done it. So, let me say that I have an eigenfunction, well, maybe I mean this operator A would have several, I mean in principle an infinite number of eigenfunctions. So, I need some notation. Let me say that psi 1, psi 2, etc. I mean this is a list, it goes to infinity, these are eigen functions of the operator A. What it means is that if A operate upon psi 1, the answer is going to be psi 1 itself multiplied by the corresponding eigenvalue, which I will denote by the symbol small a 1. And if it operated upon psi 2, the answer is going to be a 2 times psi 2, or I can generalize and say, okay, if A operated upon psi I, the ith eigenfunction, the answer is going to be A subscript I multiplied by psi I. Right. This is how the eigenvalue equation would look like. And what is it that I want to prove? I want to prove that all AI's are real numbers, they cannot be complex, that is what I want to prove. So, how will I prove it? The answer is actually extremely simple. Okay. Well, what I am going to do is, you see, in this equation that I have, this is guaranteed, if the operator A is Hermitian, this is guaranteed. So, in this equation what I am going to put is this psi, I am going to put it as psi subscript I. This psi I am going to put it as psi subscript I, because what do I want to have? I want to have A operating upon psi I, right, and this phi also I am going to identify with psi I. Suppose I did that, what will happen? This psi is going to be identified with psi I, then I will have A operating on it, and then here I will have psi I star, right, and then I would have the volume element d2, and I have to integrate over the entire space. And the fact that A is a Hermitian operator implies that I can do the same thing here on the right hand side. So, instead of phi, what would I have? I would have A operating upon psi I, because phi is identified with psi I, and this psi is identified with psi I itself. So, I would have psi I star, and then the volume element d2 integrated over the entire space, and then I will have the star, right. So, all that I am doing is, this is satisfied by a Hermitian operator for arbitrarily acceptable psi and phi. So, I just say that these are both, this psi and phi are both the same eigenfunction of that operator, that eigenfunction being psi I, right. So, if that is the way it is, what will happen to the left hand side? A operating upon psi I is going to give you the corresponding eigenvalue, which is small a I, which is just a number, multiplied by psi I, then I have to multiply by psi I star d2 integral, right, that is the left hand side. And what will happen to the right hand side? There is this star, this A operating upon psi I is going to do exactly the same thing. I am going to get A I, then psi I, then psi I star, volume element d2 integrated over the entire space. But now you look at this, this is just a number. So, therefore, you see here I have integration with respect to position coordinates and so on, but a number does not depend upon position coordinates. So, I can just move it out, and therefore, what will happen? I will have A I coming outside, then integral d2 psi I star psi I, right. And if your wave function is, if your eigenfunction is normalized, then this will actually be equal to unity. At the moment I will not say it is normalized, because I do not need it, okay. And what will happen to the right hand side? See, this A I is a number, so I can just move it out of the integral sign, I will have it here, but then I have to take the complex conjugate. So, what will happen? I will have A I star, and what do I have left? I would have left integral d2 psi I star psi I, the whole thing complex conjugated, right, and this complex conjugation I can take it inside if I like. So, if you took it inside, what will happen? I will have psi I star star, double star is equivalent to doing no starring. So therefore this star and that star I can remove, but when I take the star inside, it is going to get here. So that is what happens. And then when you look at this, you would realize that this integral and that integral, they are the same, right. If they are the same, I can just remove them, and so what is the result? I get the result that ai is equal to ai star. What does that mean? Any given eigenvalue is equal to its own complex conjugate, and this can be valid only if ai is a real number, right. If ai is a complex number, this will not be satisfied. So therefore, any given eigenvalue ai has to be real. So that is a very general result, and this is the reason why in postulate number 3 we, was it in no, it was in postulate number 2. In postulate number 2 we said that the operator has to be Hermitian, because the eigenvalue is guaranteed to be real, right. In postulate number 3 we talked about measurements, and we said that if I make a measurement, the answer has to be an eigenvalue of the corresponding operator, right. And we know that when we make measurements, the answers that we get are real numbers, right. And therefore, it is necessary that the eigenvalues should be real, and for a Hermitian operator, the eigenvalues are guaranteed to be real. So this is a general result. I will prove one more general result later. Thank you for listening.